Thank you for having me. My name is Toub. I'm a partner software engineer on the .NET team at Microsoft. I spend most of my time focused on the libraries that make up .NET, but also sort of up and down the stack with other people, really thinking hard about the performance and how we evolve it moving forward in the future. .NET has been going through something of a performance renaissance. It's been around for 2 decades now, and for a large portion of its existence or its youth, performance was always a consideration. It was always important, especially at the lowest levels of the stack. But other things often trumped performance. For example, usability would often be really paramount. Obviously, security is always and continues to be first and foremost, but usability would end up taking precedence over performance to the point where we might not expose something because we were concerned about someone maybe not using it correctly, or we might make something not quite as fast as it could be in order to make it a little bit easier to use. And with .NET Core, over the last, say, 5, 6, 7 years, we've really revisited that and made sure that performance is right up there with security and safety as being the most important things. Now, usability absolutely is critical. But when it comes down to deciding, do we make this slightly less usable for something slightly more, something faster? That's a conversation that we have now, whereas previously it generally always went in favor of usability. Performance does end up being key at all levels now of everything we do in the stack. .NET is open source. We get dozens of PRs every day, and every single one of them, whether it came from folks that work on the .NET team, whether it came from folks elsewhere in Microsoft, or whether it came from folks in the broader .NET community, every single one of them is viewed through a performance lens. Even if it's a bug fix, it's very likely that one of us will comment on it saying, hey, I'm wondering about this aspect of perf, can you share some benchmark numbers? Because we view everything through the lens of performance. On top of that, we're also spending a huge amount of our time building features that are very much end-to-end engineered for performance, not just thinking about performance as part of some other feature, but actually building features explicitly focused on performance such that a developer can take advantage of them and make their apps scream. One of my favorite things about all of this, and we'll talk about this a little bit more when it comes to open source, but the .NET community really gets to vote with their feet. Meaning, it used to be that if you working on your application hit some sort of performance bottleneck in some .NET class, and you wanted to make it faster, you had to write up your issue, somehow get it to the relevant folks at Microsoft, have it find its way to a program manager thinking about the next version of .NET, have that be prioritized and triaged, and eventually find its way to a developer who might be able to work on it for the next release in 2 years or whatever it may be. But with .NET Core, you can clone the repo, find the area you want to improve, make the change, submit a PR, and it could very well be in a nightly build the next day. Which also means that all of us are spending a good portion of our time actually collaborating and reviewing a lot of these PRs that are coming through. So a good portion of my time is actually spent thinking about perf, not in terms of my own changes, but in terms of other people's changes. So it's a really exciting time. I've described a lot of this over the years in some blog posts. If you haven't read them, there are links here. I'm not sure if I can distribute this deck after the fact. I'm happy to, so you can click them. But you can also just search for these titles and my name online, and they'll pop up in Google or Bing or your favorite search engine. Around .NET Core 2.0, I was realizing, looking back over all of the perf improvements that had gone into the various .NET Core releases, and realizing we hadn't really talked about it much. So I took a stab at summarizing some of the key changes that had got into the release. And it got a lot of good feedback. So for .NET Core 2.1, which while being a quote, dot release or a minor release, it was actually a pretty substantial major release. I spent a lot of time going through and documenting a lot of the performance improvements that had gone in. And along the way, I try and also sort of educate the reasons that the changes were made and why they helped and what the trade-offs were and so on. Then again for .NET Core 3.0, again for .NET 5, and sometime in the next few weeks, I'll probably sit down and start working on a .NET 6 post. Since we're currently working on one of the last previews for .NET 6, which is due out in the November timeframe. So after this talk, if you haven't read them, I'd humbly encourage you to go read them. I think they're pretty extensive. They're fairly long, and hopefully educational in one way, shape, or form. All of these changes, the ones in the blog post, some of the ones we'll talk about today, they really exist for two reasons. One of which is we really want you to be able to take your .NET application, let's say it's on .NET Core 3.1, and change your CS proj to update to .NET 5 and have everything just get faster. Like, that's a key goal. We want to be able to, you don't have to rewrite a line of code. We want you to be able to either recompile or just redeploy and have everything get better. On top of that, we also want you to be able to do a little bit of work and take advantage of new functionality that is, again, explicitly focused on performance. And so you can upgrade, get benefits, write some code, get benefits. And those same APIs, we also then try to use wherever we can within the rest of the stack, such that those existing APIs benefit from the new ones. And so a lot of the changes we're going to be talking about today fit mostly into the former category, as do most of the things I've talked about in the blog posts. But this kind of is the scope of the changes that we work on when it comes to performance. Now, various changes we'll look at are about this or that change we made to the code. But I would argue that the most impactful change, bar none, that we made for .NET Core versus .NET Framework was distribution vehicle, which might seem a little strange. You don't normally think of how you deploy bits as impacting the runtime throughput or memory consumption of those bits, but it's been absolutely critical, and for one key reason. .NET Framework is distributed as part of Windows. That means that however billions of machines out there are running Windows, those billions of machines are running .NET Framework, and there is one per box. So whatever version of .NET Framework is on the box, every application on that machine is using that framework, separate from VMs and the like. If we make a change to .NET Framework as part of a patch, as part of a new version, and we push that out, every machine that gets that automatically picks up that new behavior. Every app is now running against it. And at that scale, no matter how safe the change you've made you think is, you are going to break someone, guaranteed. To the extent that we have made changes in the past that were 100% functionally correct, all they did was make something significantly faster. And that still, quote, quote, broke people because, for example, in this one case I'm thinking of, they had a latent race condition in their code, had never manifested because the area of code that would have caused the race condition simply wasn't fast enough. We made a change, we improved performance, we pushed it out, and all of a sudden we're getting calls about how Microsoft broke this customer's application simply because we had made something faster and the race condition started triggering in their application. But there are also cases where we simply have made changes and there have been subtle corner case niche bugs, and they have, again, broken people. In fact, there's a fairly famous case from around 2008 where in the late March, I think early April timeframe, we pushed out an update to .NET Framework and broke printing in TurboTax. And if you're in the United States, you can probably guess that the one application you don't want to break during tax season is TurboTax. You think we'd learn from our lesson, but no, in 2012, we did it again. And to this point, we basically try and avoid any patches other than critical security patches to .NET Framework during US tax season. So we're extremely careful now about what kinds of changes we make to .NET Framework. And we've basically announced that while we are going to continue supporting .NET Framework and shipping security updates and patches for a very, 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 very long time, it's also not where we're investing. We're investing in .NET Core. It's where all the new functionality is going. It's where all the new perf improvements are going. It's where all of our primary energy and thought is going. The reason I say distribution vehicle matters here is because largely .NET Core is side by side. On the same machine, you can have .NET Core 2.1, .NET Core 3.1, .NET Core 5, .NET 6 preview, whatever we just released, preview 5. You can have all those on your machine at the same time in different applications. Excuse me. Different applications can be targeting different versions. So if there's a breaking change that went into a version, you don't have to upgrade to it until you have adapted your code to handle it. On top of all that, you can actually ship your own private copy of .NET Core with your application, which means you're totally walled off from anything that might have been done on the machine, and you get to choose exactly which bits you use. And in fact, there are even benefits to doing that. If you do want to deploy in that manner, you can then trim or tree shake your application such that anything from that framework that's not being used just sort of evaporates. And you get it down pretty small. For example, with the new WebAssembly support we have in Blazor for Blazor WASM with .NET 6, I think the number is a sort of the default template app for Blazor WASM is something like 1.5 or 2 megabytes for the entire application and framework, everything that kind of heads down to the browser. So lots of different mechanisms, and all of this means that our risk tolerance is way higher. So breaking changes, still a very big deal. We still think about them very thoughtfully, but we do make them. We also have a much higher tolerance for churning the code base, because even if something creeps in, there are mitigations that end users have. They can choose to wait until we fix an issue. They can choose when they roll forward, when they move to a new version. So all of this means we do large, massive rewrites. We do lots and lots and lots of small tweaks, all with the safety of knowing that our distribution vehicle enables this in a much better fashion. So distribution vehicle has been key for performance. The other thing that I alluded to earlier that's been absolutely key for performance is open source. There are only so many of us at Microsoft that actually work on .NET itself, but we want the broad community at large to benefit from the broad community at large. So if you look at, for example, the blog post that I wrote, this was around July of last year, on performance improvements that had gone into .NET 5 since .NET Core 3.1. The post at that point covered around 250 PRs focused on performance. That was a minor subset of all the PRs that had gone into release. And it wasn't even all the ones that were focused on perf. Between July and when we actually shipped in November, I think there were another 30 to 50 perf-focused PRs that actually made it in. But the key thing here is more than a fifth of them were actually from folks outside of Microsoft. And then there was another percentage from folks outside of the .NET team, and obviously a large portion from the .NET team itself. And if you look at what I'll be writing about for a .NET 6 post, it already has way more than that, which is really exciting. Now, sometimes these performance improvements are things that impact everyone. For example, there was a change, I think it was in .NET Core 3.0, that went in from one of our prolific external contributors that helped with how much time we spend doing some zeroing of stack frames in support of making sure the GC is able to do its job correctly. This is something that impacts every single method that you call. And he made it faster by employing vectorization to do the zeroing faster. Sometimes they're still significant, but way more niche. So for example, an external contributor was found spending a lot of time doing color conversions using the drawing color class and was able to submit a perf improvement for some of those conversion methods. And then there are other things where sometimes they're entirely experimental. For example, the Bing team wanted to play around with using operating system large pages as part of their application. And when it added experimental support to the GC, we reviewed it, we got it merged, and now it's an option for everyone to use, still experimental, but anyone can throw the flag and try it out. And we love all of this. So if you haven't contributed to .NET Runtime or .NET ASP.NET Core or .NET WinForms, and you're interested, I'd highly encourage you to. We love the contributions. They benefit everyone. So those are sort of two big areas of changes. But obviously we take many changes. And so the question is, how do we decide what we're going to take? Well, one way we do that is just focusing on data, micro benchmarks. So we've standardized basically on benchmark.net, which we use for measuring micro benchmarks on pretty much everything. And anytime you submit one of these PRs and we have a question about performance, we'll ask you for some benchmarks that demonstrate what it is you're trying to improve, or maybe have you tested this to see if maybe that's regressing. We also have a full regression suite of benchmark.net based benchmarks that we run on a continuous cycle. If you haven't used it, super easy. .NET add package benchmark.net, goes up to NuGet, downloads the bits, updates your project file, and then you can write an application like this. This is my entire program. This line of code here is basically telling benchmark.net to find all of the benchmarks that exist in my application, of which I only have one right now. And that one benchmark is just taking a field, storing it in int32 and calling toString on it. So this is the benchmark to see the performance we have for formatting integers into strings. I can run this using however complex a command line I want, but right now I'm saying I want to run this in a release build. I want to target the lowest surface area that I care about. In this case, that's .NET Framework 4.8. I want to run all the benchmarks, and I want to run it on .NET Framework 4.8, .NET Core 2.1, .NET Core 3.1, and .NET 5. And benchmark.net is going to proceed to run this benchmark an appropriate number of times on all these platforms, doing all the statistics it needs to do to separate the noise from the signal, and end up spitting out lots of interesting information, including results like this. These are the results I got on my machine. And you can see in this particular benchmark, .NET Framework 4.8, it was taking us about 48 nanoseconds to format this 1, 2, 3, 4, 5 value into a string and allocating about 40 bytes. A few years back when we released .NET Core 2.1, that cost was cut in half from 48 nanoseconds to 22 nanoseconds, still allocating the same amount. When we moved to .NET Core 3.1, we got a tad faster, but we also shaved 20% of the cost of the memory off the operation. And then for .NET 5, the performance doubled again, getting down to 11 nanoseconds. So we can really see the progression, lots and lots of changes in each release, something as simple as int32 formatting improving every single release of .NET Core, and that continues. Other things we measure, we don't just look at micro benchmarks, we also look at, say, industry benchmarks. So Tech Empower is a key one that we focus on. This is a set of web server focused benchmarks, web service focused benchmarks. We pay attention to different ones every release. For a long time, we were focused on the plain text benchmark, which is sort of just how fast can you send and receive the smallest possible response you can think of to the server. And you can see that ASP.NET over, I don't know how many of the previous rounds, has been in the top positions, tied for basically #1 with any number of other frameworks. But for example, in the last release, we picked 2 specific benchmarks. For .NET 5, we really wanted to improve our standing on the JSON serialization benchmark, which, while it does involve JSON serialization, is really another request response. And then also the Fortunes benchmark, which is about a request coming into a web server that then contacts a backend database as part of the request and response. And you can see for the Fortune benchmarks, for example, we had 2 entries with 2 different database providers sitting behind it, or sorry, 2 different transport layers sitting behind it. But they were both approximately the same, about 280,000 requests per second. This is on Linux. And you can see this in the rankings, this put us at about 24 or 26, depending on which transport we were using. When we moved to .NET 5, you can see that 280,000 requests per second. In the official numbers, went up to 400,000 requests per second and jumped ASP.NET to be in the top 10. So these are the kinds of things we're paying attention to. And there are many, many changes where a PR will come up, and either we'll ask the contributor if they have access to our backend test systems to try it out with Tech Empower, or we'll take it ourselves and try it out with the various Tech Empower benchmarks to see if and how a particular change may positively or negatively impact the various benchmarks that we're looking at. Obviously, you know, we care about performance on benchmarks, but at the end of the day, there's some reason we're trying to improve the performance of something. Sometimes we want to improve the user experience. We want requests to make it to the user faster so that they show up faster. We want to be able to allow more users at the same time so that people aren't timing out or whatever. We want the user interface to be snappy, but it can also just be, at the end of the day, saving dollars, right? If I can do more with less, if I can get things done faster and use my machine for less time, I can use that machine for something else, and this can translate into real dollar savings. So one of the things I focus on is various internal and external systems where I'm able to sort of see, waving my hands, how many cores are being used for some duration of time in the execution of particular functions. When that number reaches something like, say, 1,000 or 10,000 or 20,000, I start to really pay attention to, wow, this is really an area that we should go and invest, because at the end of the day, that's going to save everyone lots of money. And to David's previous comments about the environment and CO2, it's going to keep a lot of emissions out of the atmosphere. So for example, in the last release in .NET 5, regex was something that was popping, that was really showing up as being used by lots of folks, Microsoft and non-Microsoft, in Azure, out of Azure, as being a real consumer of cycles, of CPU cycles. And so it's an area we invested. So I grabbed this regex off the net. This is a regex for parsing emails. And a simple example here, just looking for someone at example.org. Again, this is with the benchmark.net syntax. So just paste that into the previous example I had and see if this particular address matches with this regex. And we can run it again on .NET Framework 4.8 and then .NET Core 3.1 and .NET 5 and see the kinds of improvements that went into the release. So for example, on .NET Framework 4.8, we were taking about 470 nanoseconds. Then on .NET Core 3.1, between the few years in between there, we managed to shave off about 20% of the costs. But then for .NET 5, we were able to cut that by another third or so, getting it down to 148 nanoseconds for this particular operation. That is a huge savings when it comes to CPU cycles and the money we're spending on these resources. If you've got an app and you're paying per core in Azure and you can do it with 1/4 the cores, that's going to make you pretty happy, and it's going to make your budget pretty happy. Another example in the sort of 1,000 cores club from recent releases is compression. Compression shows up in all manner of workloads. So here, a little benchmark, it's grabbing, I think I grabbed the complete works of Mark Twain from Gutenberg as a text file. I'm compressing it as a setup step. I'm compressing it into a stream. And then the benchmark is just repeatedly decompressing it and seeing how fast we can decompress that. Ran this on .NET Framework 4.8 and ran it on .NET 5. You can see we get about 20% faster. We also dramatically reduced the amount of allocation required, going from 350K down to basically nothing. But what's really interesting about this is, I mentioned we're very careful about what the changes we make to .NET Framework 4.8, to .NET Framework in general. This one was so impactful. The improvements that we made to compression were about 3 or 4x previous releases. This was so impactful and showed up in so many workloads that this .NET Framework 4.8 number actually includes having backported this particular set of performance improvements back to .NET Framework, just because it was of that order of magnitude. This is one of, I don't know, I can probably count on one, maybe two hands, the number of performance-focused changes that have gone back from .NET Core to .NET Framework, but this was one of them. So this is, for .NET 5, this is 20% on top of that 3x gain that was already ported back. So these are, we think of compression and regex as being sort of meaty examples. There are also things we're spending just a whole lot of time simply because the sheer number of times you invoke them. So for something like dictionary, right, shows up everywhere. And you expect something like try get value to be so fast that who cares about how much it costs? It's going to be so fast, it doesn't really matter. But you do that millions and millions and billions of time, any performance improvements there actually add up. And so it's an area where every release, and again, I mean the broader we, because a lot of contributions here have actually come from external sources, external to Microsoft. We have every release driven down the cost of operations on dictionary. So for example, .NET Framework 4.8, you can see this particular example is basically doing 1,000 lookups, 1,000 ordinal ignore case lookups on strings in the dictionary, summing them up, returning that value. So that was taking about 16 microseconds on .NET Framework 4.8. We halved that for .NET Core 3.1, getting it down to about 30 microseconds, and then shaved off another 30% on top of that for .NET 5, getting it down to about 20 microseconds. So we make changes to things that are big, and we make changes to things that are small but used a lot. And just one more example, since we talk about the web and UTF-8 is very prevalent on the web. Something like UTF-8 encoding ends up being used a lot, and is part of this, what I term the thousands of cores club. And so this benchmark here, all I'm doing is I'm turning a string into an array of bytes, then going back to a string. And we can see on .NET Framework 4.8, This was taking about 190 nanoseconds on my machine, and we more than doubled the throughput down to about 80 nanoseconds for .NET 5. And all this stuff continues to just get faster for .NET 6. So there are many ways that we have achieved these improvements. And again, I mean the broader we, I'm not just talking about folks at Microsoft, but all the contributions from folks at Microsoft and in the broader .NET community. Sometimes it's via complete rewrites, and these are the kinds of things that we would always shy away from in .NET Framework for fear of any kind of compatibility issue. But for example, concurrent queue. Concurrent queue first shipped in .NET Framework 4.0, and it was a good implementation, but it wasn't a great implementation. And so for .NET Core 2.1, we completely rewrote it, focusing on the kinds of costs, the kinds of use cases, the kinds of scenarios we saw concurrent queue being used in, with a particular focus on, for large scale, reducing synchronization costs, and most importantly, reducing memory usage. We got it to the point where it was so fast, we were able to throw away threadpool's queue and replace it literally just with concurrent queue. So now the system.threading.threadpool, its global queue is a concurrent queue of T. And we can see why. If I have a little benchmark here, I've got a concurrent queue of ints. I spin up two tasks. They both wait for each other, so they start at the same time. One of them then queues a million integers, and the other one tries dequeues, spins until it can dequeue all 1 million of those integers. We can see on .NET Framework 4.8, this particular benchmark on my machine was taking about 45 milliseconds and was allocating about 8.5 megabytes of memory. And on .NET 5, we dropped that by 4x down to 11 milliseconds and basically got it to allocate nothing. So from 8.5 megabytes to a few hundred bytes for this particular benchmark, which is pretty great. Sometimes it's not about doing complete rewrites. Sometimes it's being thoughtful about the algorithmic complexity that's being used in these various various operations. So for example, in link, we can see in this benchmark, I've got some data in an array, and I'm sorting it, and then I'm going to skip the first 10, and I'm going to grab the first thing after the first 10. And previously, this operation would have done a full sort, an order n log n sort, and then skip through the first 10 and then return that element. But we can actually pass data from the order by to the skip to the first, which is actually where the execution happens. And the first operation could say, interesting, you're doing an order by, but you only care about one value. So I can do, instead of doing, say, a full sort, I can just do a partial select to only zero in, to only sort the pieces of the data that I need to find the one value that's critical, changing the algorithmic complexity and the amount of work being done. And you can see that then drops me, in this particular example, from 3.7 seconds to about 200 milliseconds. And that difference would grow dramatically the more data I threw at it, to the point where I probably couldn't even put it on the screen because my operation wouldn't have finished in time. So sometimes it's complete rewrite, sometimes it's algorithmic complexity, and sometimes it's totally changing the way we write our code. So for example, in .NET Core 2.1, we introduced span, and this has been a complete game changer for the code that we write throughout the .NET stack, permeating all levels of the stack, from the runtime all the way through up ASP.NET Core and to applications on top of the runtime and the core libraries for developers that care about performance. What is span? Well, I'm using a little bit of made up C# syntax here because today in C# you can't actually express what span is. You probably will be able to in a future release of C#. But essentially span is a tuple of a ref and an int. So it's basically a pointer, just a managed pointer, like if you were passing a ref to a function, except this one happens to be a part of a struct, and a length. So basically we're referring to some contiguous piece of memory where it starts and then a length. And I can use a span to represent a string. I can use a span to represent an array. I can use a span to represent some data on the stack. I can use a span to represent some native memory. So I can represent all these different things with one type so that I can unify all of my logic around all of these data types. And that type is fully safe just as array. So it's fully bounds checked and all that. And then I can do really interesting operations on this. So the conversion to span is 0 allocation. Indexing, and I can index just like I can with array. I can slice it in an allocation-free manner, since all I'm doing is moving the pointer and changing the length. I can also reinterpret this. So with an array, if I had an array of integers and I wanted an array of bytes, I would have to allocate a new array of bytes, copy over the relevant data, and then use that. With spans, I can just reinterpret, effectively a reinterpret cast like you had in C++, reinterpret that span of integers as a span of bytes, and then continue to operate on it. And then throughout the framework, there are hundreds upon hundreds upon hundreds of methods now that operate on spans, in addition to strings and arrays and so on. All of this gives us performance and safety, and in a way that we're able to leverage throughout pretty much everything that we now do. On top of that, there are now optimizations, more and more optimizations in the JIT focused on the spans, so that certain patterns that developers write are now hyper-optimized, whereas previously with arrays they may not have been. And also optimizations showing up in things like the C# compiler itself for generating more efficient code when you use spans because of certain constraints the compiler can trust based on it. So let's just take one simple example here. We've got a function here where I'm taking in a quoted string, and I want to say hello to that person's name, in this case Stephen, by stripping off the quotes. So I have to do a substring operation, and then I concatenate hello and the substring. I run this on .NET Framework 4.8 and .NET 5, and you can see it's nice. We're maybe 15% faster on .NET 5 already, but we can do better than that. So if I wanted to use spans, I could, for example, first stack allocate a span. And you notice I don't have to use unsafe here because the C# compiler trusts that if I'm storing a stack alloc directly into a span, that is a safe operation. I'm not directly accessing a pointer. I can copy the literal hello into the span. I can slice that string as a span, the name string, to slice off the quotes, copy that to the output, and then I can finally return the relevant portion of that span as a string. Now I run this on .NET 5, and we see that 22 nanoseconds drops to 18 nanoseconds, but I've also cut my allocation in half. But now we can say, all right, well, that's nice, but that's a lot of code, some complication there. Couldn't we wrap that up into helpful functions that I could reuse? And so we end up exposing things like an overload of string.concat that accepts spans. And now I can write almost the exact same code, shorter even than the original code, just using spans and slicing them. And now not only do I allocate half the amount, but I'm more than double the throughput that I had in the original code. There are also other significant benefits to span. One of the things that we've done that we focused on as part of these pervasive coding changes is we've actually focused a lot on moving code that was in C and C++ into C#. And this might be counterintuitive. Most people think, oh, C and C++, they're way faster than C#. But there are many cases where that's simply not true, and many reasons for that. We can look at an example of this. In .NET 5, we added a whole bunch of sorting routines for spans. In fact, we took all of the code that was in the runtime for sorting arrays. It was written in C and C++. We deleted it. We instead wrote it in C#, almost entirely safe C# with just a few unsafe pieces in very constrained regions that we could, hyper focus on reviewing. Did it in terms of spans, and then we actually have array.sort on top of that. So array.sort is actually using span sorting. And we can see the impact of this. I've got a benchmark here that just fills an array with some reverse sorted numbers, then sorts it. And we can run it on .NET Framework 4.8. This particular operation was taking 95 nanoseconds. There were some minor improvements that had gone into .NET Core 3.1 that shaved about 10% off of that. But then you can see for .NET 5, where we moved this into C# and wrote it with spans, you can see it's twice as fast as what it was in .NET Framework 4.8. And there are lots of great benefits to spans, and also to this kind of rewriting that we're doing from C++ to C#. One of them is this kind of pervasive use of spans. Because the logic was in C#, it was a lot easier for us to then use spans with it. This then allowed us to not only use it internally, but expose it out for other code to take advantage of. But there are other advantages. When that code was all in C and C++, it was all sort of unsafe. It was all pointer manipulation. Whereas when we moved it to C#, as I mentioned, we were able to keep it almost entirely in bounds checked C# code and only make the one or two critical tight inner loops in a few places. I think 2 places in the entire implementation ended up being quote unquote unsafe. Another benefit of this is, a lot of the contributors that come to the .NET Runtime repo prefer working in C# than in C++. They can experiment faster given the syntax and the niceties of the language and the libraries and whatnot. And so we end up finding that more people are interested in experimenting and contributing more when code is in C#. And so we end up seeing many more PRs to further improve performance and experiment with things than we did when they were in C or C++. So it's not that C# in this case ends up being faster, it's that more time was invested in finding ways to optimize the code. At the same time, we're also, because it is safe, we're happy to accept those kinds of changes because we don't have to, or we're happy to more readily accept them because we don't have to worry about the same kind of potential security vulnerabilities or buffer overruns and the like that we would have had to scrutinize the native for. And therefore, we can spend less time doing a better job reviewing the changes and having a higher level of faith in them. But there's actually another benefit to this this moving stuff out, and that has to do with garbage collection. So for any of you who run, who do web services, and you're focused on things like, I'm running my server GC, but every once in a while it pauses for a massive period of time. And my latency shoots up. And so, my 95 or 99th percentile latency is much higher than I would like it to be. That's because of GC pause time. When the GC needs to do a lot of its work, it has to pause the world, make sure all the threads are in a stable position. Then it can do its work, and then it can allow the threads to release. But there are certain operations that you could do. Well, let me take a step back. Every time we transition from C#, like core lib, into the runtime, there's transition costs. Like when you make a p invoke, there's some overhead associated with the p invoke. When we transition into the runtime, there's some overhead associated with that. And for certain really fast operations, we try and eschew as much of that overhead as possible by cutting some corners. And sometimes cutting those corners means that the GC isn't able to do as good a job of interrupting those threads as we would like. And we can see an example of that here. So I've got a little application that is spinning up a background thread, and all it's doing is sitting in a tight loop, sorting an array, which which is always going to be sorted. So it's just very fast, try and sort it, already sorted, try and sort it, already sorted, in and out of managed code between C# and the runtime when the sorting code was in native. And then I've got my main thread is 10 times, it's forcing a garbage collection, and then it's sleeping for about 15 milliseconds, forcing a garbage collection, sleeping for 15 milliseconds. So because I'm doing this 10 times, you'd expect it to sleep for 15, 16, 17, 150, 160, 170 milliseconds. And then the GC is going to take some time. So let's round it up and guesstimate that this is going to take about 200 milliseconds to run. But I run it on .NET Core 3.1, and I get similar results for .NET Framework 4.8. And we see it's nowhere close to that. It's taking 3 seconds, 4 seconds, 5 seconds to do this operation. And the reason for that is because of those fast transitions where we cut some corners, the GC is having a really hard time interrupting that background thread that's calling into the runtime. And as such, it's having to pause the world and that main thread while it keeps trying to interrupt that background thread. When we moved all of this into managed code, the GC was able to do a much better job at managing this. And so now when we run it on .NET 5, you can see that 2, 3, 4, 5 seconds is much closer to the 200 milliseconds that we initially sort of waved our hands at and predicted. So span is sort of one very pervasive change we see throughout. Another has to do with async. So async await and tasks in C# have permeated everything everyone does. And as a result, in .NET Core 2.1, we completely rewrote the infrastructure behind async await. And you can see the results of this in a simple benchmark. Here I've got a benchmark that is 1,000 times its yielding. So it's basically awaiting something that completes immediately after the await. So it's always just sort of forcing it to post back. And just for fun, I've added an async local since that shows up in a lot of these. When I run this on .NET Framework 4.8, you can see this was taking about 2 milliseconds. When I run it on .NET Core 2.1, you can see that more than cut in half to about 920 or 930 microseconds. And by .NET 5, we got that down to about 800 microseconds. But the big thing you can see here is in memory allocation, the jump between .NET Framework 4.8 and .NET Core 2.1, we went from over 600K to about 100K allocated for this operation, which is great. And you can see why here. If I do a memory trace this is using the allocation profiler in Visual Studio, you can see all the objects that were being allocated in .NET Framework 4.8, and then in .NET 5, we just have this one allocation per iteration. So this is very nice, but we're still, that one allocation is for the task that's being returned from that yield once method. So what if we could do something about that? So in, I believe, .NET Core 2.0, we introduced value task of T. Value task of T was nothing more than a discriminated union between a T and a task of T, which meant that if you returned this from one of your async methods, and the async method completed synchronously, which is actually very common. In fact, probably 95% of all async methods end up completing synchronously. The first time you call, say, reading from a buffered stream, it's going to have to go out and do some I/O. But the next time it's got data buffered, and so that async read actually completes synchronously. For that case, we can return the T in the value task rather than a task of T and avoid that allocation. But even for asynchronously completing operations, for asynchronously completed operations, this didn't help. But we actually in .NET Core 2.1 introduced the ability to help by adding a new interface. And so not only could a value task wrap a T or a task of T, it could also wrap an iValue task source of T, which then allowed an implementation to plug in its own sort of backing object behind a value task, and in doing so, enabled it to pool it or reuse the same object over and over. And we can see this as an example using sockets. So sockets, as of .NET Core 2.1, take advantage of this because it's extremely common to do, say, very, very tight hot loop receive and send async operations on sockets, and we want those to be as allocation free as possible. So I run this benchmark, which is just doing 1,000 receives. So there's no data available. It is going to yield. Then I send some data. And then I wait for the receive because the receive is now able to be satisfied by the sent data. And we can see for this particular benchmark of 1,000 receives and sends, on .NET Framework 4.8, this was taking 35 milliseconds and allocating over 300K. And on .NET Core 2.1, you'll notice the allocation column has a dash. There is zero allocation associated with this benchmark now, because once the socket is created and the object that is being used to back these value tasks has been created, we know we never again have to allocate anything for synchronously or asynchronously excuse me, completing send or receive operations. And you can see over time then in the networking stack, we've also made further improvements. So in .NET Core 3.1, things got, throughput got better. And again, in .NET 5, things got even better. So async has been a big area where we've made pervasive changes across the stack. And you can see many more places taking advantage of these iValue task source implementations. In fact, for .NET 6, one of the likely things we have landing is both framework support and compiler support for being able to use pooled iValue task source implementation behind your own async value task methods automatically, just via tagging them with an attribute. So I'm excited to, hopefully that will land for .NET 6. One other thing that's been pervasive has been array pool. I don't have a benchmark for this, but just as an example, this is very similar to the code that we have in stream.copy2async. It used to be that we would allocate a brand new array for every time you did copy2async. Now we rent one from the shared array pool, which we can optimize to our heart's content. We rent the buffer, we use it, we return it, and in general, this drastically reduces the amount of allocation while doing better around cache coherency and not thrashing caches and the like that we might otherwise get. One more example of pervasive changes we've made, and that has to do with vectorization and hardware intrinsics. So for years now, .NET has had vector types for doing multiple operations at the same time, taking advantage of functionality in extension architectures and things like SSE, SSE2, AVX, AVX2, and so on. But we've also in recent years started adding direct access, individual access to these instructions, yielding literally thousands of new methods in .NET Core 3.0, 5.0, and 6.0. And these operations are now being used pervasively throughout the lower levels of the libraries in span and string, encoding, JSON serializer, even things like WebSocket are getting it on the game. We can see example of why this matters. I've got a little bit of Shakespeare here, and I'm just searching string.contains for a particular word in this text, doing an ordinal search. And when I run this on .NET Framework 4.8, you can see this was taking about 40 nanoseconds. This was not vectorized. In .NET Core 2.1, we took advantage of the vector types and vectorized this, and we went from about 41 nanoseconds to about 10 nanoseconds, so about 4x faster. And then starting in 3.1 and 5.0, we started taking advantage of the direct intrinsics. We got a lot of the way there with the sort of the general vector support, and then taking advantage of the direct intrinsics to eke out even more. So we went from 10 nanoseconds to 7, and then for .NET 5 to 6 nanoseconds. And so every release, we're really pushing the boundaries, and more functionality ends up using this sort of base level of performance-focused API. So that was a whirlwind tour. I am basically out of time. If I could ask two things of everyone here, it is first, if you're still on .NET Framework, please start thinking about moving to .NET Core. It's where all of our energies are going. It's where all of the performance improvements are going. It's where all the new functionality is going. It's where the world is moving. So if you haven't gotten there, totally understandable, but please be thinking about it. If you are already on .NET Core, please stay current, because as you can see, every release just gets better and better and better. And staying current also then means that you have a better chance of contributing issues that you find, you can come help us fix, and you can take advantage of things as soon as they're released. And then my second request is get involved. If there are things you'd like to see be better, file issues on .NET Runtime or .NET ASP.NET Core or .NET WinForms, whoever it may be. Or if there are, if you'd like to actually get your feet wet and actually try and make some PRs, we would love it. Come find things to improve, whether it be something as simple as comments or something as complicated as vectorizing some new operation, taking advantage of hardware intrinsics. Whatever it is, we would love to have you. And with that, I will say thanks.